very happy to have Anton Bernshteyn to tell us about minimal subdynamics.
Thank you. Thank you, Spencer. Thank you, everybody, for coming. Right, so we're talking about minimal subdynamics, and all of this is joint work with George.
If you want to put on the microphone.
Do I?
Also, no one has asked you. And also, the no living room. So.
Okay, where do I have to? I can put it in my pocket or something.
You can also ask us.
This how it works. This is gonna work. You turn it on. But this is there a way to make it like it is green, so it is on. Is it on?
Yes, it's on.
Oh, okay. No, that's great. Are we on air? Okay. Yeah, that's too much. Let's see if this is gonna work. All right. So, that's 1 minute. 89 more to go. So yeah, so this is all going to be joint work with Josh Frisch. And let me right away introduce the main character in this story. The main character is gamma, which is an infinite countable group. So for the rest of the talk, that's what gamma is going to stand for. So the title of my talks is the word dynamics. So we're going to be studying dynamics of actions of this group gamma. And which countable group, you may ask? Any countable group. Any infinite countable group whatsoever. And that, in some sense, is one of the points of this talk. So you may have heard this famous saying attributed to Gromov, that any statement about all countable groups is either trivial or false. So my hope in this talk is tell you some things about all countable groups that are true and hopefully non-trivial. And really, in some sense, it's out of the questions that I'll be addressing are sort of very classical and would have definitely made sense already in the, say, 50s and 60s, where the study of dynamical systems and topological dynamics in particular, and the form in which we understand it now started, they would have already made sense then. The techniques to address them really have only appeared recently, in maybe past 10, 15 years is sort of the period of time that the scale of time that we're talking about. And what's exciting about it is that these techniques, although they address classical dynamical questions, they actually come from descriptive set theory. Or really, they come from two sources, combinatorics and descriptive set theory. And it's the mixture of the two that has the powerful effect of answering questions, where you don't even need to worry about what group you're working with. But since this is a set theory seminar, I figured I should start with some set theory related things, then talk about dynamics, and then return back to the set theory in the end. So that's what I'll do. So we'll start with a little set theoretic taste of set theoretic results. So it's all descriptive set theory. So that's what I mean by set theory for the purposes of this talk. And then we talk about the general dynamical problem that underlies it. Right. Okay. So to start with, we have our countable group gamma. And as I said, we want to think about it dynamically, so we want to study actions of gamma. The thing is, if you don't know anything about the group to begin with, what actions do you even have? Of course, if it's some particular group that you like, then it has maybe it has some nice actions that you like. But if it's an abstract group, I guess what can you do? You can maybe look at the action of gamma on itself by multiplication. Well, that's not very interesting. Well, I guess you can say the study of this action is group theory, but it's not really very interesting from dynamical perspective. And in some sense, there's not much else you can do. So the one general construction is just a slight generalization of this, where instead of a group acting on itself, we're going to make it act on its power set, which I'm going to denote by 2 to the gamma. So this is the power set of gamma. So it's all the subsets of gamma. And I'm going to think of this as a topological space with pointwise convergence topology. Meaning that the sequence of sets converges if for every element it either is eventually in or eventually out. So really this is the familiar Cantor space, but indexed by the countable group gamma instead of the natural numbers. And what's the action? If I take a group element, little gamma, and I want to act by this group element on a set A, so here A is a subset of gamma, what do? I just shift every element in A by gamma. So it's the left multiplication, but I'm multiplying every element in the set at once. So this is the set of all products of the form gamma delta, where delta is in A. All right. And this is called the shift action of gamma. Okay. So this is a very important example for two reasons. One is when we study dynamics of group actions in general, a powerful approach is to actually relate them to this particular action that is you can understand, you can get your hands onto it. But the other reason is that if a group is completely general and you don't know anything about it, that's basically the only thing you can do. So in some sense, this is an important example because for general groups, we don't really have any other ways of constructing examples other than looking at this and maybe looking at some invariant subsets here, and then you're restricting the action there. And one thing that people in descriptive set theory have been doing is trying to understand the orbit equivalence relation here. So an important example in the theory of countable Borel equivalence relation is the orbit equivalence for these types of actions. Actually, I would like to zoom in on the part of the space in which the action is free. So I'm going to denote it as by free of 2 to the gamma. So this is the free part of the shift, which is the set of all subsets of gamma such that are moved non-trivially by every non-identity group element. So gamma times A is not equal to A for all non-identity group elements gamma. Yeah, so this is a proper subset, of course. For instance, if A is the empty set, it's a fixed point of the action. So we remove this, but this is still large. So this is co-meager into the gamma, for example. And now we want to understand sort of the Borel structure of the orbit equivalence relation here. One thing you can do to get your hands on it is to study sort of how the orbits of this action in this space intersect different Borel sets in the space, right? So let's say B. So this is a subset of the free part of the shift. Let's suppose it's a Borel complete section. Complete section. Okay, well, what does mean complete section? It means that it intersects every orbit. So it meets every orbit. Yeah, so if I remove the word Borel here, if I just say, oh, it's a complete section, it's a subset that intersects every orbit, I can use the axiom of choice, for instance, to pick a single point in every orbit. That would be fine. But it's exactly the sort of thing you cannot do definably. You cannot do that in the Borel way. And moreover, it's a fairly basic exercise to show that you cannot, in a Borel way, even pick just finitely many points out of every orbit. So an easy fact is that I guess let me put it this way, there is some point in this space such that the intersection of B with the orbit of X is infinite. Yeah. I guess X here is a subset of gamma. I switched, let me write it A. It's A. But it's not gamma. it's, I move this, I think of this as a point in the space. I move it by every single group element. I'm not doing literally I'm not multiplying every group element by every element in A. That would be silly. Yeah, so that's why I want to write it as little x, so that we don't get confused. Yeah, so there is an orbit in this action whose intersection with B is infinite, if B is the Borel complete section. And this is an easy descriptive set theory 101 exercise. Yeah. What is not easy is the following theorem of Gao, Jackson, Cron, and Seward. When did this appear? Maybe 22, something like this. Is that actually there is more. So this says that there is an orbit such that the intersection of this orbit with B is infinite. Actually, this infinite intersection also you can require it to be in some sense dense inside of the orbit. So the technical term is B is syndetic in some orbit. Okay, what does that mean? This means that there exists a finite set, we call it F, subset of the group, such that if I take this set B and I move it by these finitely many group elements, this union contains an orbit. So there's an orbit of some point that is fully covered by these finitely many translates of B. That's what's happening here. And this is what it means to say that B is synthetic in this orbit. Or to put it another way, so this is your orbit. If you take any point, and maybe this is B. If you take any point in this orbit, you can move it into B by using one of finitely many group elements. Right. So this is not at all easy anymore. Right. And this is a very useful fact about the general geometry of these Borel complete sections and how so if you try to understand sort of the combinatorics of this orbit equivalence relation in relation to Borel subsets of the space, this is a very useful fact to have. And in fact, oftentimes, if you want to have really finer information about the structure of this relation, you want to put some extra constraints on this finite set F. Maybe you don't want to use all group elements to find such a finite set F, but only some subset of them. So for instance, for one of the applications in their paper, they were considering the case where gamma is specifically Zn for some n, and they wanted the elements in F, which are now tuples of natural numbers, to have the sum of the entries be odd somehow. And that was relevant because they had some parity argument later on after this, right? And so they had to, and they proved that you can arrange that in that particular case with sort of a special argument for this setting. So you can ask, can we in general kind of classify for which sets F can you guarantee such a thing? Yeah. So I have my Borel set B, which is a Borel complete section. What are the finite sets F such that a set of the form F times B captures an orbit of the action? And yeah. Right. This is, I guess, let me write it this way. Sigma times X, where sigma is in F and X is in B. Yeah. So it's a union, in this case, it's a union of finitely many translates of the set B. Yeah. Right. So, okay, so here's the theorem. It turns out that there are no constraints on the set F. Well, okay, it's not that it's true for every finite set F, of course, but for every large enough finite set. So if B a Borel complete section, then there exists some natural number n such that for every set F of size at least n, f times b contains an orbit. So the geometry of the set, sort of how it sits inside the group, is completely irrelevant. As long as you have any union, to put this yet another way, if you have a Borel complete section, any union of sufficiently many translates of B is going to cover an entire orbit of the action. Okay. Any questions so far? So, well, if you look at this looks like some sort of compactness theorem if you kind of squint, because I'm saying that for every object there exists a natural number with some property. So I'm extracting something finite out of the object I'm starting with. And indeed, the key to understanding this result is to study actions of gamma on compact spaces. This is a statement, of course, about the free part of 2 to the gamma, which is not compact. It's not a closed subset of 2 to the gamma. But the way you understand this theorem is by thinking about compact sets, compact spaces. So let's kind of remember this, but put this to one side for a second, and let's talk now about actions on compact spaces and topological dynamics. Right. So what is topological dynamics? It's exactly this: is the study of continuous group actions on compact spaces. So the key definition here is the notion of a gamma flow. Is a continuous action of gamma on a non-empty compact Hausdorff space X. Let's see. So when I say the action is continuous, my group is discrete. It's a countable group and it's discrete. So what I'm really saying is that every group element is interpreted as a homeomorphism of X, autohomeomorphism of X. Right, non-empty compact Hausdorff. For the purposes of this talk, it is sufficient to think about the case when X is metrizable, so Polish, second countable. But I was told that for this audience, this is actually making people less comfortable than thinking about compact Hausdorff spaces more generally. But it doesn't make a difference for what I'm going to be talking about. All the spaces that will appear explicitly as examples will be metric spaces. Right, non-empty is fine. The key thing here is compact. So the theory would have a completely different character if we didn't require the space that the group is acting to be compact. Right, so what are some examples? Okay, 2 to the gamma, on which gamma is acting by shift. This is a compact space. Again, maybe I should highlight this. This is not an example because this is not a compact space. It's a Polish space, but not compact. But of course, again, if you know something about the group, you can cook up some other examples that are natural. Maybe I should give you one more example. Say gamma is Z. So it's a cyclic group then. And to describe an action of Z on some space, I just need to describe a single transformation, a single homeomorphism of the space, and then I'm just iterating it. So for instance, let's say, as a standard simple example, let's take some theta, which is a real number, and define a transformation of S1, which is the circle, given by rotation by a fixed angle, rotation by theta. Yeah, so that's my autohomeomorphism of the circle. And then I have the group Z. I can extend this to a group action of Z on the circle by saying that n times x is the nth iterative of the rotation operation acting on x. So you rotate by theta n times. Yeah, that's also an example. Okay. a gamma flow X is minimal, this is a classic and sort of very important notion. It's minimal if it has no proper subflows. No proper subflows. This is a sensible thing to define, but what is a subflow? Let's think about this. So a subflow of X is a subset of X that is itself a flow. So it has to be a non-empty. It has to be invariant under the action of gamma so that we can restrict the action to this subset, gamma invariant. But also it needs to still be compact. In other words, it has to be a closed subset of X. Yeah. Okay, let's think about some examples. Let's think about this rotation flow. Yeah, so it's a specific case, gamma is Z, and my flow is Z acting on this circle by rotation by theta, where theta is fixed. Is this minimal? Active learning. Is this minimal? Or when is this minimal? Maybe it's better to say.
Depends on theta.
It does depend on theta. Yeah. Yeah, so this is minimal if and only if. Yeah. So theta is, I guess if we're measuring things in radians, it should be an irrational multiple of pi. Yeah? Yeah, exactly. So this, I think this is due to Dirichlet or something like this. And the easiest way to see this is not actually to think about subflows, but let's think about sort of what is this, the non-existence of a proper subflow, what does this tell me in terms of points rather than subsets of the space? You see, if I, again, let's forget the closed bit for a second. If I didn't require things to be compact, if I take any point in the space and I take its orbit, this is a non-empty gamma invariant subset, right? So if I didn't require things to be compact, the minimal sets would just be single orbits, yeah? But there is this closedness condition. So if I take an orbit, I need to take the closure of it. That's the smallest set that can contain this orbit and be a closed set. And what should happen is that this closure just gives me the whole space X back, if X is minimal. So X is minimal if and only if every orbit in X is dense. Yep. And so now if you think about rotation by the angle theta, this basically says if I start with some point and I start rotating it by theta and I start iterating this operation, will I get a dense subset of the circle or not? If theta is rational multiple of pi, I will return back to the starting point after finitely many rotations, and then so I get just a finite orbit, which is not dense. But and I think this is something that Dirichlet proved in 18 something or other, that if you do rotate by an irrational, if you do an irrational rotation, not only do you never return to the starting point, but you get a dense subset of the circle as a result. Right? Okay, good. Yep. Right, so this was for the group gamma being equal to Z. What about general gamma? I mean, I guess do minimal flows even exist? Well, I guess there are some. Maybe it's easy to come up with one example of a minimal flow, a fixed point, a single point in which the action is trivial. There's certainly no proper subset, non-empty subsets, let alone subflows of this. But there's a more general fact that sort of tells you that there should be lots of them. And the fact is that every gamma flow has a minimal subflow. So there are lots of these guys. But the proof of this is, well, the proof of this is somewhat unfortunate. It's Zorn's lemma. That's how you do it. You know, if you have you take your flow X. If it's minimal already, great. If it's not, it has a proper subflow. Is that minimal? If yes, great. If not, it has a proper subflow. Because the space is compact, intersections of decreasing sequences of closed sets are closed and non-empty. And so in the end, by Zorn's lemma, you're going to get an actual minimal subflow in there. Which is great, except that it tells you nothing about what they actually are. And it's, in general, very hard to construct examples of minimal flows with properties that you want. A lot of problems in topological dynamics are about what properties can be realized by minimal flows. So for instance, I mean, let's think about, I don't know when I say this example. What about minimal subflows of 2 to the gamma? So 2 to the gamma itself, first of all, is that minimal? Is this minimal? Let's think about this. Active learning. Is it true that every orbit in 2 to the gamma is dense? So if you take any subset of gamma and you start shifting it by different group elements, you get a dense set. Is this true? It's not true. Why not? What's a point that doesn't have a dense orbit? The empty set. Yeah, exactly. No, this is not minimal. For instance, because it has fixed points. Empty set, there's also gamma itself. So both of these are fixed points, which means that the singleton just containing gamma is a fixed point. And certainly the orbit is not dense, it's just a single point in this big uncountable space. Yeah, so, but this theorem tells us that there are minimal subflows here. And, well, there are at least 2 minimal subflows that we can easily list, namely the singletons containing these fixed points, right? So these are examples, but these are boring. Are there non-boring minimal subflows? And the Zorn lemma doesn't tell you anything about non-boring objects. And indeed, it actually is really quite non-trivial to construct non-boring minimal subflows in 2 to the gamma. So there's this result of, I guess the first result of this type in this level of generality is the theorem of Glasner and Ouspensky from 2009, which what they showed is that 2 to the gamma has an infinite minimal subflow. Which is a prerequisite for being non-boring, yeah, for an object. And I want to highlight the year. So all of these notions, people have looked at them since, as I said, 50s and 60s really is kind of the time where I think this general framework has solidified. So until 2009, apparently we didn't even know that there exists an infinite minimal subflow into the gamma, yeah? A much harder, so this is not too difficult. A much harder theorem is the result of Gao, Jackson, and Seward. That really is the starting point of this modern study of topological dynamics using descriptive set theory and combinatorics. This is, I think, 16 maybe, it's a reasonable date for this, is that 2 to the gamma has a free minimal subflow. Okay, what does free mean? Meaning that it's contained in the free part of the space. So the action of the group on the subflow is free. Has every non-identity group element moves every point. So free, just to say, means every non-identity group element moves every point. So of course such a thing has to be infinite. And I'm putting minimal here as in parentheses because actually what they do is they prove that there exists a free subflow, which then by Zorn's lemma has a minimal subflow inside of it, which also will have to be free. So actually we don't get much of a handle on the minimal flow we get in the end here out of this construction still. But such a thing exists. Okay. Let's see if I said everything I wanted about this. Yeah. Okay. So yeah.
There can be closed and containing free parts.
Exactly. Yes. Yeah. Yes. That's the point. Yeah. So the subflow X is contained in the free part of 2 to the gamma. So this is a non-empty gamma invariant set that is closed in 2 to the gamma, but contained in this density delta, like strange looking set, the free part. Yeah, exactly. So there's one more thing I want to say now, because we're going to be returning to this, is, I mean, what does this have to do? So I started by talking about this theorem, which does, okay, so I guess what's in common between these two things? There is the free part of 2 to the gamma, and there is a subset of it, yeah? But actually, there is a little bit more that you already should be able to see is related. It's because there is a third way of equivalently describing what it means for a flow to be minimal. So flow x is minimal, and this is, I guess, fact. If and only if, for every non-empty open set U, subset of X, I'm just write it like this. Every non-empty open set U is synthetic. I.e., there exists a finite set F, subset of gamma, such that F times U is X. Why is this? So I mean, I will not show, the proof is easy, so I will not write anything. But the reason this holds is because of compactness of X. Because X is minimal, this means that every orbit is dense. In particular, if you give me an empty open subset of X, every point can be moved to U by some group element. But because of compactness and openness of U, this actually implies that there is some finite set of group elements that's already enough for this. And this is what the syntheticity condition says. So hopefully this seems like it's relevant for that part of the theorem. Right. Okay, any questions about this? So, another question? Everything's clear so far? Yeah. So what is minimal subdynamics? The title of my, I'm getting now to the title of my talk. So far we've been talking about minimal dynamics, somehow, minimal flows, and whether they exist. Here's a question. Again, this is a very natural, very sort of fundamental question in this theory. I'm going to call this the minimal subdynamics question. Okay, so say you have a subgroup of gamma, infinite subgroup. Is there a free gamma flow? You can relax free to something else, but I want to have it to be non-trivial, and free is sort of as non-trivial as possible for my purposes. X. That is, so look, what is a gamma flow? It's this compact space, and the group gamma is acting on it. But delta is a subgroup of gamma, so if I just restrict to only looking at the elements in delta, this in particular is a delta flow, right? Does there exist a free gamma flow X that is minimal as a delta flow? What does this mean, in other words? Right? Every delta orbit should be dense. It's a free action of gamma, but to get a dense set, you don't need to use all the group elements from gamma to generate your orbit. It's enough to look at the delta part of the orbit. Yeah. So of course, such a flow has to be minimal as a gamma flow, but this is a stronger condition, because maybe gamma is a huge group we're just passing to. Maybe I have one generator that's of infinite order, and I want that generator to already witness minimality. Yeah, does such a thing exist? Very natural question. Surprisingly tricky. So, well, again, if the group is very, very simple, namely Z, then it's easy to answer. So let's just think about this. If gamma equals to Z, then this rotation by an irrational multiple of pi is minimal with respect to all non-trivial subgroups. And this has to do with the fact that an integer multiple of an irrational number is still irrational, right? Because the subgroups of Z are just the k times Z for integers k, and you just get different rational rotation. That's basically until very recently that okay. There was also the similar construction for Zn. And that was all that people knew until 2020s, which is strange. And I guess you can say this, we understand these things because these are abelian groups, and when things need to commute with each other, maybe things are a bit easy here. And that is witnessed by the first general result along these lines, which is due to Anti-Zucker. A few years ago. I think this appeared also in 2022, something like this. If gamma, so what he showed is that if gamma is a product of two infinite subgroups, then the answer is yes, for delta. Right, so if gamma is a product of delta and some other infinite subgroup delta prime, there exists a free action of gamma where delta is acting minimally. Notice that the situation is symmetric. There is also a free action of gamma where delta prime is acting minimally. This construction cannot make both of them act minimally at the same time. These are two different spaces. And he asked in his paper, can you make both of them act minimally simultaneously? So the answer is yes, and this is the best previous result on this, as due to Frisch, Sewer, and Zucker. Or maybe. Here's what they showed. So much stronger statement. Suppose you have an infinite countable family of infinite normal subgroups. Then there exists a free gamma flow that is minimal with respect to every delta n. Okay. Yeah, so that's pretty good. That's quite impressive. And you see, very crucial for the proof is this assumption that these are normal subgroups. This somehow is the smallest trace of commutativity that's enough for the proof to actually go through. So in this sense, it's really generalizing this line of reasoning that uses the fact that things commute enough. I guess things here don't literally commute, but at least your subgroups are normal that you're looking at.
Why would it actually be infinite if you only have finitely many normal subgroups? Is it still true?
Yeah, I'm not assuming that these are all distinct. Yeah. Yeah. If you just have one subgroup, you can deal with it. Even if you have an infinite family that you want to take care of at the same time, it's still fine. Yeah. Right. Okay. So what's the main result of this talk? Here's what we did. So the question is, can you get rid of the normality assumption? I mean, of course, normal subgroups are nice and all, but most subgroups aren't normal. If you take a subgroup at random, it's probably not going to be a normal subgroup. In particular, what somehow even the following wasn't known. If you take, say, the free group on two generators or something like this, and you take one element of this, can you find an action of this free group where this element is acting minimally? Right, because this element isn't going to generate a free subgroup, so this doesn't work. So the answer is yes. What we were able to do is get rid of this normality assumption completely. Actually, we did more. We also can get rid of the subgroup assumption. So let me explain what I mean by this. The philosophy here is that you should forget about group theory. Everything is really about the combinatorics that are so soft they shouldn't care about group theoretic structure at all. about subgroups, let alone normal subgroups. So definition. Say S is just a subset of gamma, not a subgroup, just a subset. I'm going to say that a gamma flow X is S minimal if you can probably guess, instead of saying that, I mean, it's the same thing as here. This part of the orbit that is generated by moving only by elements from S is dense for every point. If for all X in X, the set S times X is dense. Yeah. So if S is a subgroup, this recovers the previous notion. This is equivalent in the same way as in general X being minimal classically is equivalent to saying that every non-empty open set is synthetic. This is equivalent to saying that every non-empty open subset of X is S synthetic. I.e., there exists a finite subset of S rather than of the whole group, such that, and I guess I should be writing F inverse times S is equal to X, S times U is equal to X. Yeah, so it really what's happening is we're restricting which finite sets we're looking at. It's not arbitrary finite subsets of the group, it's finite subsets of S. If I phrase it this way, I can push things even further. Because what I really need is a collection of finite sets to choose from. They don't necessarily have to be just all finite subsets of a given infinite set S. So we're going to say that if the curly F is a family of finite subsets of gamma, then I'm going to say that X is F minimal if every non-empty open U is F synthetic, meaning that there exists a set F in this family such that, I guess I want to be consistent with this, F inverse times U is X. Okay. So what's happening is I'm generalizing first from subgroups to subsets, arbitrary subsets, and then further actually from having a single set S, just having some family of potentially completely unrelated to each other finite sets. And I just want to say that for every open, one of those finite sets works. Yeah. Does it make sense? Yeah, the definition. So now I can state the result. Very good. Yeah. Right. So I have my group gamma. Let's say I have, okay, what is this? This is a sequence of not necessarily distinct, countably many families of finite subsets of gamma, such that for all n, so I want some kind of non-triviality assumption here. For all n, if you look at all the sets in the nth collection, their sizes are arbitrarily large. Then there exists a free gamma flow X that is Fn minimal for all n simultaneously. And why did I leave a little bit of a space here? Because actually you can also make it to be a subflow to the gamma if you so desire.
From your introduction, there's no other space where you would try to construct it.
Well,
But,
I mean, I like a little bit because you can also do this, which is a genuinely different space. And actually, this is where we construct it. And then there is a separate argument that pushes it into the, yeah.
Putting required.
Yes, yeah. And right, yeah, yes, yeah, exactly. So this, I mean, this is fun, right? Because this indicates this is a strengthening of this result I mentioned before, right? So Gao, Jackson, and Seward show that there exists a free minimal subflow of 2 to the gamma. We say there exists a free subflow that is minimal in this sense for any choice of these fn's. Yeah. So for example, that's just to make this clear what this can mean in practice. If you actually go back to subgroups, right? This in particular means that if you give me countably many infinite subgroups, I can find a gamma flow, free gamma flow that is minimal with respect to all of these subgroups at the same time. So for instance, a countable group has only countably many finitely generated subgroups, so you can make it minimal with respect to all finitely generated subgroups at once. Right, so there exists a free gamma flow that is minimal with respect to all finitely generated subgroups. Yeah, so there is a little bit of what is still not, there's some kind of borderline part. We actually have to think about group theory probably, which is why we didn't figure it out, of where can you just say for all subgroups, right? You remove finitely generated, and you just want a gamma flow that is minimal with respect to all subgroups at once. Well, so for instance, oh, sorry, infinite, of course, for all infinite finitely generated subgroups. Yeah, that's important. Right, so if you want it to be minimal with respect to all infinite subgroups at once, and you do have uncountably many infinite subgroups, and moreover, really what the problem is having uncountably many subgroups that are infinite but locally finite. That's the issue. Because if you have an infinite subgroup that has an infinite finitely generated subgroup, you're fine if you're minimal with respect to the finitely generated subgroup. Right? So now the issue is if you have these, is the locally finite groups are the problem, the ones where all finitely generated subgroups are finite, but the group itself is infinite. And then, so you may hope maybe the answer is yes always, but this is not true. So there are some examples. If your group is a direct sum of cyclic groups of order infinite to many cyclic groups of order 2, something like this, there doesn't exist a free flow for this group, which is minimal with respect to all of its infinite subgroups at the same time. So some restrictions are needed at any rate, but any countable collection of infinite subgroups you can handle for sure. Okay, any questions? Right, so what does this have to do with this? I claim that this statement is an easy corollary of this theorem. Wait, so I will not do the proof in detail, but I'll reduce the proof to basic descriptive set theory exercises. Specifically, exercises in Baire category. So, forcing, if some people, if there are people who prefer that terminology, right? So proof sketch of this. Suppose not. So what is our setup here? We have a Borel complete section in the free part of 2 to the gamma. And I claim that there is some natural number n such that if you take any, if you move your set around by any n group elements, you're bound to capture an entire orbit. Suppose not. What does that mean? It means that for every n, no matter how large n I pick, I can find a set Fn, subset of gamma of size n, such that Fn times b does not contain an orb. Yeah. Did I negate quantifiers correctly? I think so, yeah. So for every n, there is some finite set that witnesses that this n doesn't work. This is a set of size n. But if I move B by the elements of Fn, I don't capture an orbit. Okay, let's take the following family of sets. I think I need to put an inverse here. It's a collection of finite sets whose sizes go to infinity. Yeah. So by the theorem, I can find X, a subset of the free part of 2 to the gamma, which is F minimal. Right. So here it's exactly the question about this. I only have a single. So this is the theorem applies to infinite to an intercountable collection of families of finite sets. Here I'm applying this to just a single family of finite sets. That's enough. And now we just work inside of X. So here's the chain of implication. B intersection X is a complete section in X. A Borel complete section inside of X. So here's the first baby exercise in Baire category theory. It means that B intersection X is non-meager. I guess because otherwise the entire space would be meager because you cover the space by countably many translates of it. Okay, so now it's not meager, it's Borel also. Borel sets are Baire measurable. In other words, this is basically open modulo meager. This is open modulo meager. Every non-empty open set is F syndetic by assumption. So what follows from this is that there exists some set F inside of our family, let's call it Fn, such that if you move this set by Fn, okay, so if this were open, I could just say it's equal to X. But this is almost open, so this is almost equal to X. So this is comeager in X. And again, the same as this arrow. A comeager set has to contain an orbit because its complement is meager, so it cannot be a complete section, right? So contains an orbit, which is a contradiction because we assume a set doesn't contain orbits. With this set Fn times B. Okay, that's it. Yeah.
So what are the F inverses? You put the inverses on there.
Yeah. This is because when they define being synthetic, so that things somehow could. It's the most unfortunate thing about all of this is that half the time things need to be with an inverse and half the time not, and you have to commit to which half you want to not have an inverse in. So somehow the way I define syntheticity is like being S synthetic, being F synthetic, is that if you move it by the inverses, you get it this way. So that's why I had to put inverse here, so that here it comes out without the inverse. Yeah. Okay.
So this Fn is the inverse of that.
Oh yeah. So yes. Yeah. This is Okay. Good. Very good. Yeah. I am very glad to see that people are actually paying attention. Okay. How are we doing? Oh, great. Any more questions about that? Yeah. So I'm kind of galloping over the Baire category stuff, but it's really easy. It's 2 lines. All of the implications that I'm missing here. Right. And there are various other applications of this as well, both in descriptive set theory and in dynamical systems that I won't go into because instead I'd like to spend the rest of this talk giving you some idea of what goes into the proof. Because I promised that the proof also somehow relies on descriptive set theoretic machinery, or at least perspective, and I hope to be able to get to that point. Right. Okay. So the proof has several moving parts, so I won't try to explain everything in detail, or try to explain everything in any form. But I want to highlight maybe two sort of big ideas that go into it that I think are quite interesting. And one idea that is, it's more of a topological dynamics idea, I guess, but it's very much inspired by or informed by descriptive set theory, as I hopefully will be able to explain later on, is this. And it's kind of surprising, I think. As I've been highlighting the whole time, the main difficulty is that we want our spaces to be compact. These flows have to be compact spaces. That's why it's hard to find these minimal flows with the properties you want. If you just wanted, say, a Polish space where every orbit is dense and blah, 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 you can, like, take the free part of 2 to the gamma. Well, maybe not the free part. Look at all the points in 2 to the gamma whose orbits are dense. This is a dense G delta subset of 2 to the gamma. If you just pass to this is a Polish space where every orbit is dense. The moment you forget about compactness, everything becomes very easy. So the hard thing is compactness. 90% of the proof, we're working in a non-compact space. So idea number one, work with an interesting non-compact space. It's Polish. It's a Polish space. So no, but not compact. And it's a very particular space, which probably has lots of other nice properties. So let me try to explain what the space is. Okay, what's the so definitions? Let's say phi is a finite subset of gamma. Okay, the Kelly graph of gamma with respect to the set. So this, I imagine this is familiar to people, but just to remind you, so the Kelly graph of a group with respect to some finite subset, which doesn't have to be a generating set for me, just some finite subset of the group. So I'm not assuming that gamma is finitely generated in particular. So it's a graph. It's an undirected graph whose vertices are elements of gamma. So the vertex set is gamma, and edges are sets, pairs of this form, where gamma is a group element and sigma is an element of the special set. Yeah, and I hope I wrote it correctly because I actually inverted everything somewhere along the way, so from how I usually do it. But hopefully this is the right multiplication on the correct side. Right. So what I'm saying is that for each group element gamma, there is one edge sticking out for every element of phi. You can multiply by all of them. This gives you the edges. Right? Right. People know this, right? This is. Okay. So but just to be completely certain, let me draw an example for, say, gamma being z squared. And phi being the usual generating set for z squared, so 1, 0, 0, 1. This is the Kelly graph. Yeah. Now I'm going to say that the set, say S subset of gamma, is free finite if all connected components of let me write this and then I'll just say in words what this notation means. This is the subgraph of the Kelly graph induced by the set S. Okay, our finding. in other words, what's happening, S is some subset of gamma. What I do is I only restrict my attention to the vertices in S. I delete all the other vertices together with their incident edges. So maybe my set S is, this part and this part, this, something like this. So when I zoom in onto S, I throw away everything else. I get this little square here, little edge here, a single vertex flying around there. So in this picture, the components of the set S are finite. Then I'm going to say that S is a phi finite subset of gamma. And a phi separator is a set S subset of gamma such that both S and its complement, gamma minus S, are phi finite. Okay. So what does this mean? This means that the set itself should consist of finite connected components. And when I say finite, they can be arbitrarily large. So they don't have to be uniformly bounded, just finite. So sort of finite chunks that are unrelated to each other. But if I look at the complement of S, if I now delete S and look at what remains, that should also fall apart into finite chunks. So in this picture, maybe I need to have some part of the set S that's sort of surrounding this window, something like this, to make sure that this part now that's inside there is finite. Yeah, this part, the blue bit of the picture, which is a big but finite connected component. Right? And things sort of have to be nested. In this picture, things have to be sort of nested in this way. So both S and its complement fall apart into finite chunks. Does it make sense? The definition. So combinatorial definition. A little exercise is first to show that these things always exist. They always exist a separator. And moreover, actually, they form a dense G delta subset in 2 to the gamma. So a generic set is going to be a separator. Essentially, because if you commit to some finite part of how S looks, then generically there's going to be some finite ring that separates it from the rest, and it itself is, and the same in the complement. Yeah. So, but because I'm not saying what is the sizes of these finite components, I'm just saying they're finite. If I look at the set of all separators inside of 2 to the gamma, that is not a compact set. So I'm going to call this SEP of phi, the subset of 2 to the gamma. This is the space of all phi separators. Yep. It's invariant under the action shift action of gamma. I guess maybe if you think about this picture, if you take this whole picture and you shift it somewhere, finite things will remain finite. So it's invariant, but it's not compact. And then I'm going to, so the main space that we study is just SEP without any parameter, is defined as the product of these over all finite subsets of gamma. Equipped with the product topology and the diagonal action of gamma. This is a cool space. I highly recommend this space to people who want to play around with topological dynamics. In particular, the proof of our theorem, the heart of the proof, is the following fact about this non-compact space. Yeah, I should maybe say. Well, I moved it up there already. Yeah. Bring it back here. Just to simplify everything, I'm going to assume from now on that gamma is torsion-free. This is not a necessary assumption. What it simplifies is that the action of gamma on this space is a free action. So actually what we need to do in general, if there are torsion elements in gamma, is that you need to pass to the free part of the space. And then things become a little bit, you just have to keep track of whether or not you're still in the free part every time. So let's just assume that the group is torsion-free, and then we don't need to do anything. This is a free action. Okay, does the definition of the space make sense? This is the main character here. So here's the main theorem, really, is that this space is what we call amply syndetic. Okay, what does this mean? Okay, actually, we define it as something stronger than what I will write. It's like, but it's a slightly weaker form, but this is enough for what I'm about to say. So here's what properties has. For every non-empty open set U, there exists a natural number n such that, okay, there's going to be a few changes of quantifiers, I apologize, but such that for all sets F, subset of gamma of size at least n, there is a continuous gamma equivariant map pi from the space to itself. It's a bit weird, but I'll explain to you why this is the right thing to do, such that pi inverse of U is F syndetic. Okay. Okay, so this is a mouthful, maybe. So what's happening? Let me draw a little picture that will explain nothing, but will look a little bit more pleasant. So here's my space, SEP, and here's another copy of it. And inside here, I chose some non-empty open set U. What I want to do now, given this, is to find a map pi from the space to itself, a self-map that is A, continuous, and B, gamma equivariant. So it commutes with the action of the group. It's a homomorphism of group actions. Such that, so one way to think about this is to imagine the image. So the image of the space under this map. Right? You map the space into itself. You sort of fold it into itself somehow. In this image, U has to become syndetic with respect to F. Right. So now U is F syndetic in this image, which is equivalent to saying that if you pull the set U back, pi inverse U is F syndetic in the space, which is how the theorem is phrased. So it's some sort of way of making an, so it's not true that every set U is F syndetic with respect to every large enough set F, but you can make it F syndetic by sort of shrinking the space a little bit, by mapping it into itself. Okay, does this make sense? Let me give you 10 seconds to process this. Even if the statement makes sense, it maybe is not clear to you why this is useful for anything. Let me explain this with another picture. This. So pi has to be a continuous map, and it has to be equivariant with respect to gamma. So meaning that if gamma pi of gamma times x is gamma times pi of x. So it commutes with the group elements. Yeah? So it preserves the action. And it has to have this extra property that it makes a given open set syndetic. And it makes it, and I guess now there's more quantifiers, right? Syndetic with respect to any large enough finite set. So for any large enough finite set, you can find such a map that makes it F syndetic for that particular F. That's the point.
Gamma equivariance forbids you from doing something silly like taking a constant.
Right, exactly. Yeah. Yeah. Yes, yeah. So it has to preserve the group action structure, actually. Yes, I guess it's the morphism in the category of gamma spaces or something like this. It has to actually be a reasonable. I mean, the equivariance is why I said that saying that U is syndetic in the image of the map is the same thing as saying that pi inverse of u is synthetic in the original space. That's because of the equivariance. Okay, so now proof sketch of what? Of the fact that there is, so what do we, yeah, how should I put it? So now, okay, it's a sketch. We want, let's just take a single family for simplicity. So F, a family of finite sets, finite subsets of gamma with unbounded arbitrarily large sizes. So the supremum of the size of the set in F is infinite. And we want an F minimal free gamma flow. Yeah, so I'm going to ignore for this sketch the issue of making it a subflow of 2 to the gamma. There's a separate argument for this. So let's just understand how we can find a free minimal gamma flow. Yeah. Here's what you do. Step 1 is you find, so we're going to work with the space SEP. We're going to find a continuous gamma equivariant map. I'm going to call it pi 0 from, essentially what's the issue with SCP? It's not compact. I want to compactify it. So I start by mapping it into some compact space in a continuous equivariant way. You say Y, where Y is a free gamma flow. So it's compact. This can be done. This is not too difficult. This is a standard construction. How you do this. So you find some sort of way of sending this space into a compact space already, continuously. So you should imagine that this is just sitting here. Why some sort of compactification? Except that it's not quite an abstract compactification because I also want it to be Polish, or second countable actually, with what I will use, which is the same thing as Polish for compact spaces. And we have this. Okay, so this is our starting point, as you can guess, because I'm calling this pi 0. Yeah. So, okay, so this is the picture. Right. Now, I will look for my F minimal flow inside of Y. The thing is, Y is already free, so all subflows of Y are also free. So I don't actually need to worry about freeness. It's the minimality that I need to worry about. How can I use this map to get some nice subflow of Y? Let's just take the image. You say, images under continuous maps of Polish spaces don't even have to be Borel, let alone compact. Sure, let's take the closure. Yeah. So now this is a closed gamma invariant subset of Y, so it's a free gamma flow. If it's F minimal, we're done. Maybe it's not F minimal. Why is it not F minimal? Well, maybe there is some open set, let's call it U0. This is a non-empty open set sitting inside of Y that when you intersect it with the space, you still get something non-empty, but it's not synthetic. And because it's not synthetic, that shows that this isn't minimal, yeah? And just as in that diagram, saying that this isn't synthetic is the same as saying that it's free image here. This set just happens to maybe not be synthetic in SEP, and that's a problem. There's a continuous map, so this is an open set. We can apply our ample syntheticity condition to get a map pi 1 from SEP to itself, such that now if I take the preimage of this under pi 1, which hopefully is this, is now it's an open set here, which moreover is F synthetic. Oh, let me just say curly F synthetic. Why can I do this? What the theorem says is that we can, we can find such a map such that preimage of a given open set is synthetic with respect to any finite set that's large enough. My family curly F, it conveniently happens that the only thing I assumed about it is it contains sets that are large enough. So I can apply this lemma to get this sort of situation. Yeah. So what I did is I made this set, open set, synthetic now. But if now instead of the map pi 0, I need to look at this composition.
not pi one dependent on a single f, right?
Yes. Yeah. So exactly. So what you do is you take this open set. The theorem gives you an n large enough. From f, you pick from this curly f family. You pick any set you want that's large enough, and that's the one you use. Yeah, exactly. Okay. So now on the side of subflows of y, what is happening is I have a little bit of a smaller subflow here, which is obtained by taking the image of this composition. What do I do next? Well, maybe there is some other open set I need to worry about. So now I pull it all the way down here, apply the same reasoning again, and get a second mount, pi 2. So I have this maybe y1 here. Now all the way here, I get pi 0 composed pi 1 inverse of y1. That's sitting here. Now I want to make that synthetic. And so I pull it back further here and you know, but now the set is synthetic. And now I have a further subflow here. And then you continue doing this. Because y is second countable, there's only going to be countably many open sets to worry about. And after iterating omega many steps, I get this nice decreasing sequence where I eventually have taken care of every open set. What do I do then? I just take the intersection. The intersection of all this decreasing sequence of closed subsets in the compact space is a compact space. And then you show that basically because of how the construction was done, it is going to be every open set, non-empty open set now is F synthetic and Lubin. Yeah, does that make sense? Any questions about this? Yeah. So this is, I mean, I'm skipping over some steps, but the actual argument is not much more complicated than this cartoon that I've shown for this. And really, the fun idea is using these self maps to propagate the chain in this way, and then taking compositions, and then on the side of y we get this intersection. And you can actually show more. So you can show that there are lots of minimal subflows inside of y with the properties you want. That sort of thing. Yeah. So what's the hard part then? It's proving this. So really, this is what the proof is all about. Is making this to work. Yeah. Okay. Good. So how do we prove that? So somehow, given this open set U, I want to find a map from SEP to itself such that pre-image review is synthetic. Yeah. How can I control where the pre-image review will land? Well, actually, that turns out to be not too difficult. So I need another definition. I'm going to say that the set, the A subset of this, doesn't have to be this space, but it's the only space I'm applying this to. This set is D spaced for D some subset of gamma if D times X intersection D times Y is empty for all X not equal to Y in A. Okay, this is if you do anything with these sorts of constructions on group actions, this is the thing you use all of the time. So the picture is, this is your set, this is the set A, this maybe is a point X. You look at this finite set that you obtain by moving X around by elements of D, and you want these little finite sets to be disjoint pairwise for all the elements in A. The lemma, which I will not say anything about how you prove it, but it should be believable, maybe, is that for every non-empty open Q subset of the space as EP, there exists some finite set D subset of gamma such that if A is open, so both open and closed, there are lots of them. It's a zero-dimensional space, and D spaced, then there exists a continuous equivariant map pi, self-map, such that preimage of U contains A. Okay, this is assuming that gamma is torsion free. So because I need the action on this thing to be free, but modulo that. Okay, so what is this saying? Again, I'm committed to my set A, and I'm just saying I really want these particular points to go to U. I want to control the preimage of U, so I want these points to go to U, maybe some extra ones, but at least these ones have to be in U. If the set of requirements like this is D-spaced for some sufficiently large finite set D, then you can do it. That's what this is saying. And this is you do it by hand somehow. It's a little bit of combinatorics that you need to do to make this work, but this hopefully makes sense. Somehow when the set is D-spaced, these requirements don't interact too much with each other, and that allows you to actually construct the map. So what is now the thing that remains to prove? Is that for every finite subset of gamma, there exists some n such that if F subset of gamma has size at least n, then there is a Clopen D-spaced F synthetic set A. So if you agree to this, we're done also, right? Because what do I do to prove this ample syntheticity condition? You give me this open set U, this lemma gives me a finite set D. I apply this to D, so now if you give me any large enough finite set, I can find a Clopen set that's D-spaced and F synthetic. Because it's D-spaced, I can cook up a map pi that sends every point from A to U. So pi inverse of U will contain A, but A is F synthetic, so this larger set is also F synthetic, and so we win. So the crux of the proof actually is this lemma. That's where the magic happens. And now I'm going to be extremely sketchy about this. This is where descriptive set theory and combinatorics meet, because this lemma really has two aspects that are in some sense unrelated to each other. There is combinatorics. Because what the lemma says that in particular there is a D-spaced F synthetic set. Given any finite set D, for any large enough F, it's possible to construct a set that is simultaneously kind of spread out. It's D-spaced, but also dense enough. It's F synthetic. This already is not obvious. Forget about all the topology, all the spaces, everything. This combinatorial fact is already non-trivial. But then secondly, there is, let me say, definability constraint. Such set can be Clopen. And this is adding extra layer of difficulty. This is where descriptive set theory becomes important. What people have been doing for the past 25 years in a lot of directions is taking non-trivial facts from combinatorics, like this type of statement, or maybe things from graph theory, questions of this nature, and trying to understand what level of sort of Borel hierarchy does the construction have to lie on, for example, or something like this. Can you do it in a Borel way? If you can do it in a Borel way, can you do it with G delta sets or something like this, right? Can you make it Clopen? Things of this sort. So we now have a large set of tools that can be used to approach this, and For the sake of inspiring you to go look these things up, I'll tell you the name of the tool that actually plays a role here. Right. The main tool is something that is called the Lovaas local lemma, or the LLL. This is something that people in combinatorics know very well and use all the time, and nobody else knows about it, which people really should, because it's extremely useful in I think in anything. Whatever you do, you probably can do something useful with this statement. And also, I don't actually know how to do the combinatorial statement without using it. So the only way I know how to prove this, forget about clopenness or anything, is using the local lemma. Unfortunately, the statement is a bit technical, so I will not tell you what the statement is. I'll draw a cartoon. So you want to solve a combinatorial problem. What you do is you take this magic wand, which is the LLL, and you wave it. And you touch the combinatorial problem with this magic wand. And what it does is it turns it into a system of inequalities in a completely mechanical way. The inequalities can look somewhat complicated sometimes, but the philosophy is that doing calculus is easier than doing combinatorics. So solving a system of inequalities should be easier. In our paper, this is the inequality we get for this. Okay. This is maybe somewhat horrendous, right? But but it's a calculation. And what you need to do now is you need to find a solution to this. Actually, if you look at this, it's not too bad, because did I just erase the lemma? Oh, well, here it is. D is the given finite set, and n is the variable, actually. So D is fixed. If n is large enough, this is exponentially small in n. This is n to the power 4. For all large enough n, this is true. So, okay, we solved it. The LLL tells you that then there is a solution to the original problem. Yeah, in a completely black box way. So, very powerful, very useful. The only question that's left is how do you make sure that the construction is clopin? And as I said, there is this history of doing things in descriptive set theory. So I'll just mention some names and finish the talk. So these spaces of separators, without calling them that, appeared in the paper of Conley, Jackson, Marx, Sewer, Tucker-Drob in 2023 under the name of asymptotic separation index. And really, you should think of this as doing interesting Borel combinatorics on the space of separators. So Borel is the key point. So making sure that the constructions are Borel. Then maybe I'll write it here. What's relevant here is that continuing this work together with Felix Weilacher, we showed that there is a version of the Borel Lovaas local lemma on this space, but which is exactly kind of what you need, except that it was Borel, and we need clopin constructions. And so with Josh, as part of this project, we actually observed really that you can make it clopin. In fact, it's basically the same proof. You just need to run it a little more carefully to make sure that things are clopin. And that's the argument in a nutshell. So as final remarks, the main takeaways are: first, sometimes if you're interested in topological dynamics, sometimes non-compact spaces contain the information that controls what's happening in the compact world, and that's pretty interesting. And the space of separators itself, I think, is an interesting example that should be explored more. And from the other direction, this sort of interaction of powerful methods from combinatorics, like the local lemma, with definable constructions that descriptive set theorists do, can be of use, I think, in a broad spectrum of directions. For example, answering questions about topological dynamics that are very sort of fundamental and natural. And I'll stop here.